You know when you're playing a game and you just stop and look around at this incredible 3D world on your screen? All the sprawling landscapes, the detailed characters, it all feels so real. But have you ever really thought about how all of that complex three-dimensional stuff, gets perfectly flattened onto the two-dimensional grid of pixels that makes up your monitor? Well, let's dive in. That is the big question we're going to tackle. How does a computer take a world that's built from pure math, with perfect, smooth lines and infinite detail, and translate it into a simple, finite grid of colored dots, and do it millions of times a second? The answer is a process that's just brilliant and incredibly fast, all born from this one key idea. Speed is way more important than perfect accuracy.
And that process, well, it's really a bridge that connects two totally different worlds, the perfect continuous world of geometry and the blocky physical world of your actual screen.
That bridge has a name: rasterization. All it really is, at its heart, is the process of converting mathematical shapes, we call them primitives, and they're almost always just simple triangles, into that grid of colored dots or pixels that you see. It's the absolute foundational step that turns an abstract 3D model into a real 2D image.
And this really gets to the heart of the challenge. On one side, you've got vector geometry. We're talking perfect lines, defined by math, that you can scale up forever and they'll never lose quality. But on the other side, you've got the reality of your screen. It's just a fixed grid of little blocky dots. Rasterization's entire job is to somehow map that perfect mathematical world onto this imperfect physical one.
So, okay, how does it actually work? The best way to think about it is like you're using a stencil. You've got the outline of your shape, in this case a triangle, and you just need to figure out which little tiles in your mosaic, your pixels, need to get colored in. It's a surprisingly straightforward process, really.
It pretty much boils down to these three key steps. First, there's triangle setup. That's where the GPU figures out the math for the triangle's three sides. Step 2 is traversal, where the GPU just zips across the pixel grid and asks a really simple question for each one. Is your center point inside those three lines? And if the answer is yes, we go to step 3, interpolation. This is where it cleverly blends the data from the triangle's corners, like color or texture info, to figure out the exact value for that one specific pixel.
That third step, interpolation, it sounds fancy, but it's really just a smart weighted average. Just imagine a triangle with a red corner, a blue corner, and a green one. If a pixel lands smack dab in the middle, it'll get an equal mix of all three colors. But if it's way closer to the red corner, its final color is going to be mostly red. That simple little trick is how we get all those smooth, beautiful gradients across our 3D objects. Now, doing that whole three-step dance for every single triangle in a scene, that would be incredibly slow. So to render these huge, complex worlds in real time, your graphics card has to use some seriously clever shortcuts. It's all about working smarter, not harder. The first big shortcut is called culling. The GPU does a super quick check. Is this triangle even facing the camera? If it's on the back of a character or it's a wall you can't possibly see, the GPU just throws it away instantly. There's zero point in processing something that's never going to be visible anyway. Next up is clipping. Okay, what if a triangle is only partially on the screen? Well, instead of processing the whole thing and then throwing away the pixels that are off-screen, the GPU is way smarter than that. It just neatly chops off the invisible part, creating a brand new, smaller shape that fits the screen perfectly. Again, this saves a massive amount of wasted work.
And finally, there's tie breaking. What happens if a pixel's center lands exactly on the line between two different triangles? I mean, who gets to color it in? To stop that pixel from being drawn twice, or maybe not at all, the GPU has a very strict rulebook. This rule makes sure that one and only one of those triangles gets to claim that pixel. This guarantees that all our models look solid, with no weird gaps or overlaps.
Okay, so we've gotten pretty deep into the technical details. But why does any of this matter to you, the gamer? Well, because every single one of these steps has a direct, tangible impact on your gaming experience. We're talking performance and visual quality. Let's just try to put the workload into perspective. A 4K screen has over 8 million pixels. 8 million! And for every single frame of your game, and we're talking 60, maybe 120 frames every second, your GPU's rasterizer has to run its tests and do its math across this massive grid. The scale is just absolutely immense. And what's really important to get is that this workload isn't linear. Jumping from 1080p to 1440p is a pretty big step up, yeah. But the jump to 4K, that's a massive leap. The number of pixels the rasterizer has to deal with just grows exponentially, and that's exactly why higher resolutions demand so much more powerful graphics cards.
This also explains something you've probably noticed while playing a game. You ever see your frame rate dip when you get really close to a big wall or a huge character model? That is rasterization in action. That object is now covering a huge percentage of those 8 million pixels, so the GPU has to generate and process way more pixel data. The load goes up, and sometimes the frame rate goes down.
Now, as brilliant and as fast as rasterization is, it's not perfect. It's an elegant solution for sure, but it's one that's built on a series of compromises, of trade-offs. And those trade-offs, they lead to some inherent limitations.
Right here, you can see the fundamental problem. The goal always is to show a perfect, smooth mathematical line, but the reality is that we're drawing it on a grid of squares. And no matter how tiny those squares get, a diagonal line will always turn into a little staircase. This compromise is totally unavoidable, and it's the source of a lot of visual quirks in rasterization.
And that staircase effect? That's what we call aliasing, or as you probably know it, jaggies. We also have something called overdraw, which is basically wasted energy, when the GPU colors a pixel that's just going to get covered up by another object anyway. Because it's all tied to a pixel grid, the image gets all blocky if you try to zoom in. And finally, stuff like glass or smoke is super complex because blending transparent colors the right way takes a ton of extra work.
At the end of the day, rasterization was the absolute breakthrough that made the fast, interactive 3D graphics we all love possible. It's a masterpiece of efficiency, built for speed above everything else, but its limits are also pretty clear. Which leaves us with one final thought. As we all push for more and more realism, what comes next? What new techniques will build on, or maybe one day, even replace the magic of rasterization?